start now. Okay. All right. Hello, everyone. Welcome back to PC Seminar. And today we have with us Shaohua Li from University of Warsaw, and he'll be talking on cluster editing parameterized about modification-disjoint P3-packings. So thank you so much for joining us, Shaohua. Over to you now.
Okay, thank you for the introduction. And hello, everyone. I'm going to talk about our paper on cluster editing parameterized above modification-disjoint P3-packings. My name is Shaohua Li. This is a joint work with Marcin Filipczuk and Manuel Sok. Cluster editing is a classical and hard problem. In this problem, we are given a graph G and an integer K. The task is to decide whether we can get a cluster graph, that is a union of disjoint clicks by at most K edits. Here edits means edge insertion or edge deletions. The triangle represents the operation of symmetric difference. That is, E triangle S equals E set minus S union S set minus E. For example, in this graph, we can delete 3 edges and insert 1 edge to get a cluster graph. The simple observation is that G is a cluster graph if and only if there is no induced P3 in G. This is an induced P3. Cluster editing is FPT parameterized by the size of the solution and also has a 2K vertex kernel. Parameterization above lower bound is a popular topic in parameterized complexity. So this question arises, is cluster editing still FPT parameterized by the difference between the size of a solution and the lower bound? Note that the size of this new parameter will decrease. Then Weber and al. Studied this line of research and showed that if the lower bound is the size of a packing of vertex disjoint P3s, then the answer is yes. In this paper, we study another variant where the lower bound is the size of a packing H of modification disjoint induced P3s. In this problem, we are given a graph G and a packing H of modification disjoint induced P3s and a natural number L. The task is to find a cluster editing set such that the size of the solution S minus the size of the packing H is at most L. Here L is the parameter. Modification disjoint means not sharing any edges or non-edges. For example, in this picture, these 2 P3s are modification disjoint. However, in the second picture, these 2 P3s are not modification disjoint because when we insert an edge here, we actually modify these 2 P3s at the same time. The size of the packing H is the lower bound of the solution because a solution S must contain 1 edit for every P3 of the packing H because of the property of modification disjoint. Komushevich proposed this open problem at Shonen meeting and also at their paper. In CEAMP, FPT parameterized by L. Here CEAMP is short for our problem. In our paper, we mostly have 2 results. First result is that cluster editing above modification disjoint P3 packing, CEAMP is NP hard, even for the case L equals 0, and when each vertex is in the input graph is incident with at most 23 P3s of the packing. The second result is that the 2 restricted variant of CEAMP parameterized by the number L of excess edits within XP. Here 2 restricted means every vertex belongs to at most 2 P3s of the packing. First, we introduce our NP-hardness reduction. Our NP-hardness reduction starts from a 3-set instance. We will show that we can construct an equivalent instance GH0 of CEAMP in polynomial time. Here, L equals 0 implies that we need to edit exactly 1 vertex pair for every P3 in the packing, and no other edits are allowed. First, let's do a warm-up exercise. Suppose we are given 2 clicks A and B, each of size 4. How can we cover all vertex pairs between click A and B using modification-disjoint P3s. This is a solution. And we can see that after covering all the vertex pairs between A and B, if we want to separate A and B, we need to delete 8 edges between A and B. If we want to merge A and B, we have to add 8 edges between A and B. Let's go one step further. Suppose we are given 3 clicks A, B, C, each of size 5. How do we cover all vertex pairs between A and B, between B and C, using a set of modification-disjoint P3s, such that we can merge A with B, separate C from AB, or merge B with C, separate A from BC, with exactly the number of the size of the packing or modification-disjoint edges. This is the solution. Let A, B, C be variables from the finite field gamma of size 5. That is with multiplication and addition modulo 5. And let A, B, C be the labels of vertices from the click A, B, C respectively. Then we create a P3 in the packing A, B, C if A minus B equals B minus C. This is part of the solution. I did not draw all the P3s here, but we will see that in this construction, every vertex pair between A and B is covered by a unique P3 from the packing, and every vertex pair between B and C is also covered by a unique vertex pair, a unique P3 from the packing. And that is, if we want to separate A from B and C, we need to delete every edge between A and B. So B and C will be merged into a click. And symmetrically, if we want to merge A and B, then we need to delete every edge between B and C. We construct the variable gadgets as follows. Let Mi denote the number of clauses that contain the variable xi. For each variable xi, we create 4 Mi vertex disjoint clicks with 5 vertices each. For every 3 consecutive clicks, we connect them in the way described in the last slide. Here, we identify K0 with K4Mi. Thus, the clicks are connected into a cycle-like structure. Because of this construction, we have to merge either every even pair of this variable gadget or every odd pair in this cycle. This choice, odd or even, will encode false or true of the value of the variable xi. For every variable xi, we fix an arbitrary ordering of the clauses that contain xi. For example, if a clause gamma j contains xi, let pi ij denote the position of gamma j in this ordering. Then we introduce the skeleton of the clause gadget for clause gamma d. In this picture, the cycle-like structures represent variable gadgets we introduced just now. These thick brown edges represent the connections between variable gadgets and the clause gadget. The green P3s belongs to the packing and keeps basic constraints. Roughly saying, for this green P3, if we delete the 2 edges here, then these 2 edges becomes undeletable because we do not allow excess edits. So these 2 clicks are forced to merge. And if we delete these 2 edges here, these two clicks, namely QD3 and TDB, have to be merged. Or these three clicks has to be merged. If we delete these two edges, then these two clicks has to be merged. Next, we introduce the merging model for clause gamma D. The merging model is a guide for clicks to merge or separate. A vertex here represents a click in the skeleton of the clause gadgets. If there is an arc between two vertices, the two corresponding clicks can be merged. And the triangle means that the three clicks of the corresponding vertices can be merged. For example, these two clicks can be merged. And these three clicks can be merged. However, these two clicks cannot be merged. Or especially, these three clicks can be merged. However, these two clicks cannot be merged. This will be important for our construction. Let's zoom in into the connection between variable gadgets and clause gadget. How do we transfer the choice of the variable? We introduced just now that the odd or true, odd or even pair of the merging will encode the true or false value of the variable xi. The solution is as follows. Now this the bottom part is the part of the variable gadget, and the top part is a click, which is the connection between the variable gadgets and the clause gadget. First to be and the red P3 in the packing. And note that the red P3 uses this edge V1 V3. However, this edge V1 V3 is already used by the by some P3 in the variable gadget, because V3, V1, and V8 is a P3 in the variable gadget. So this edge V1, V8 does not is not included, is not covered by any packed P3 now. Sorry. When we enter the second second blank P3, we use the edge V2, V4, and this edge V5, V2 is not covered by any P3 now. And similarly, when we enter the green P3 here, and this edge V6, V2 is not covered anymore. However, we can make use of these two edges, this edge V5, V6, to create a new P3 in the packing, namely V5, V6, and V2. And when we end this blue P3, this edge V1, V7 becomes vacant now. We can use this edge V7, V8 to create a new packed P3, namely V1, V7, V8. If we view every packed P3 as a triangle, because they are modification disjoint, then these triangles are edge disjoint. So we can, and we see these two parts as two parts of a bipartite graph, and we can find a C8 here. We need this C8 because later we want to cover every vertex pair between this side and this side, and we need more need to add more P3s of the packing. However, we don't want to destroy this C8 structure because we don't want to use these edges or non-edges, which is already covered by this C8. This will be useful later. Then let's go to the implementation of the merging model. Note that in the merging model, the number does not represent the number of vertices in the click. It just represents the level of this click. We will decide the exact size of every click from level 0 to level 4. The base case is that clicks of level 0 have size 5, and clicks of level 1 have size 1. And we need some algebraic tool in next step. So let P be a prime number, and let B be a complete bipartite graph, such that the size of V is P and the size of W is 2P. We need to solve the following three questions. How can we cover all vertex pairs between V and W by a set of modification-disjoint P3s, or equivalently, edge-disjoint triangles? Question 2 is, how can we avoid conflicts if we are already given some initial packed P3 or C8 between V and W? Question 3, how can we make sure that W is connected even if we remove the packed P3s, since we will use W as a building block to merge or separate in reduction? So this is the basic idea. We will partition W into two parts, W and W prime, of size P each. If a P3 W prime already exists, we will put W and W prime into two different parts, like this. If a C8 already exists, we will expand a C8 as in the following picture. This is the C8 we introduced just now, and we will expand it into these two parts. And after doing this, we will label the vertices of W prime by elements of the finite field of size P increasingly. The labeling of the vertices of C8 and P3 are in the picture. Let VA and WB, WC prime be the labels respectively. We will pack the triangle or pack the P3, VA, WB, WC prime if A minus B equals B minus C. This is the solution. And we will see that the packing coincides with existing C8 and P3. And I want to emphasize here that after we pack these P3s, these two parts, W and W prime, is still connected because in our construction, these two edges actually belong to two different P3s in the packing. So this edge, WI plus 4, W prime I plus 4, is still not covered by any packed P3. So these two parts is still connected. So let's go to the implementation with Cloud Gadget with that tool. The base case is clicks of level 0 have size 5 and the clicks of level 1 have size 1. For each click Q of level I is at least 2. Let V be the union of clicks adjacent to Q, which are of lower levels. Let P be the smallest prime such that P is at least the size of V, and we add P minus V dummy vertices to V and apply the algebraic tool. And after this procedure, we will see that this click of level 2 have size 4, and this click of level 3 have size 14. And these two clicks of level 4 have size 34. And this click has size 46. Then let's prove the correctness of this reduction. First, we show the completeness of this reduction. Suppose we are given a clause gamma D with 3 variables. If xi is true, then we merge every odd pair in the cycle-like structure of this variable gadget. Otherwise, we merge every even pair in this gadget of xi. In this clause gamma d, if xa satisfies gamma d, then we do the following operations: we merge TDA and QD1, merge QD2, QD3, and QD4. This is shown in the picture. We merge these 2 clicks and these 3 clicks. We delete all other edges. If XB satisfies gamma D, then we merge QD1 and QD2. We merge QD3, QD4, and TDB. This is shown in this picture. And we merge these 2 clicks and we merge these 3 clicks. Delete the edges here, and the edges here. If XC satisfies gamma D, then we merge TDC and QD4. We merge QD1, QD2, and QD3. Like we merge these 2 clicks and we merge these 3 clicks. We delete the edges here. And we will see that in all these operations, the number of edits is equal to the number of P3s in the packing. So this means the L equals 0. And we finally get a cluster graph. Then we go to the soundness of the reduction. For the variable gadget of xi, we will show that either every even pair are merged. Then we set xi to true, or every odd pair are merged. Then we set xi to false. And in this clause gadget, since QD1 and QD4 are connected, this means, but not adjacent. Connected means that after removing the P3s in the packing, there is still a path from QD1 to QD4. Here, there is a path here. But these 2 clicks are not adjacent. So if we want to get a cluster graph, at least one of the following 3 cases will hold. First case is QD1 and QD2 are separated. Second case is QD2 and QD3 are separated. The third case is QD3 and QD4 are separated. In the first case, QD1 and QD2 are separated. And because QD1 and QD2 are separated, and we have the following results here. This is shown in the picture. If QD1 and QD2 are separated, then we delete the edges here. So these 2 edges become undeletable. So we have to merge these 2 clicks. That is QD1 and TDA. And because QD1, this click is not adjacent to this click in the merging model we showed just now. And so these 2 clicks cannot be merged. So we have to delete the edges here and we separate this TDA with this click. And because we delete these edges here, and there is some P3 here, so these edges of the P3s are not deletable now. So we have to merge these 2 clicks, and we have to merge every odd pair in the cycle. In case 1, because we merge every odd pair in the cycle of XA, so XA is set to true, so it satisfies gamma D. In case 2 and case 3 are similar to case 1. If case 2 holds, that is, if we delete the edges here, then XB is set to false and satisfies gamma D. If case 3 holds, then XC is set to false and satisfies gamma D. We will show some pictures below. If we delete, if case 2 holds, we have to delete these edges between QD2 and QD3. And because this green P3 here, we delete this side of the edges, so this side of the edges cannot be deleted anymore. So we have to merge these 3 clicks or these 2 clicks here. For example, if we merge these 2 clicks, because this click is not QD3 is not adjacent to this click in the variable gadget of XB, So in the merging model, they are not adjacent. So we have to delete these edges here. So we have to merge these two cliques. That is, we have to merge every even pair in the variable gadget of XP. So according to our construction, XP is set to false. So it satisfies gamma D. If case 3 holds, then we have to delete these two edges. Then these two cliques, and that is QD4 and the TDC has to be merged. Then because QD4 is not adjacent to the cliques here, then we have to delete the edges between TDC and the variable gadgets. And because of the Brown structure, we have to merge every even pair in the variable gadget of XC. So XC is also set to false, and it satisfies gamma D. So at least this means at least one of the three cases will hold, and there is always a variable which will satisfy gamma D. So this completes our unpairedness reduction. Note that our unpairedness result implies that CEMP is probably not FPT or even in XP unless P equals NP. This motivates us to study a more restricted variant of CEMP, in which every vertex is listed with at most 2 packed P3s. This is the definition of this problem, which is called CEATMP. The definition is very similar to CEAMP, except that in the input graph, every vertex is incident with at most 2 P3s of the packing. And we also want to find the cluster editing set S such that the size of S minus the size of the packing H is at most L. The difference between the size of S and the size of H is at most L. And finally, we show that this variant CATMP can be solved in XP time. The main ingredient in this XP algorithm is that we show that CATMP can be solved in polynomial time when L equals 0. And next, we will introduce the algorithm for the case of L equals 0. First, we define protoclusters as the connected components of the graph obtained by removing edges of all packed P3s. We define 4 types of P3s as follows. And every ellipse in the picture represents a protocluster. This is type alpha P3. This is type beta P3. And this is type gamma P3. And this is type delta P3. And every ellipse represents a protocluster. This means the protocluster means after removing all the P3s in the packing, it is still a connected component. The first reduction rule is that for any protocluster C, if there are 2 vertices UV such that UV is a non-packed non-edge, that is, UV is not covered by any P3 of H, then we return no. This reduction rule is because it just follows from the definitions of L equals 0. Reduction rule 2 says that if there is a type beta or type delta P3, then we insert an edge XZ into G and remove the P3 from the packing. This is also not hard to prove because of the definition, L equals 0. And this is some example. If we have a type beta P3, then we insert an edge, or type delta P3, we insert an edge to this non-edge, and remove this P3 from the packing. This means the edges of the packed P3 will becomes normal edge that is not covered by any P3. Reduction rule 3 says that suppose we are given 2 protoclusters A and B. If there is a non-packed non-edge UV, This is a non-packed non-edge. It's a non-edge but not covered by any P3. And there is also a packed edge XY, such that X is in VA and Y is in VB. Then we delete this XY and remove the corresponding packed P3 from H, and this edge becomes non-packed null. Reduction rule 4 says that if there is a connected component C in graph of size and both 6, then we do brute force. Reduction rule 5 says that if there is a protocluster C which is an isolated clique, then we remove C from the graph. After applying reduction rules 1 to 5 exhaustively, if the algorithm did not return null, then there is no protocluster of size at least 4. Next, only protoclusters of size at most 3 will remain in the graph. Then we do reduction rule 6. And this is a picture. If we have a protocluster A of size 3, and this is the possible structure that will appear because of the constraint that every vertex is instant with at most 2 packs P3. So this structure is very restricted. And in this structure, we will delete the edges between B and C, because B and C are all protoclusters of size 1. And we insert an edge here and remove the corresponding P3s from the packing. Then, so our next task is to study how the protoclusters of size 2 and 1 can be combined, because there are no protoclusters of size greater than 2. Let S be the solution. And we will focus on the structures of C6, C5, and C4 in the final cluster graph after applying the solution S. And this means cliques of size 6, 5, and 4 respectively. The following is an example of the possible structure of the clique of size 6 in the final cluster graph. Because we only have the protoclusters of size 2 and size 1. And this, we will show that this is the only possibility that it can be combined into a clique of size 6. And this is a clique protocluster, this is a protocluster, and this is a protocluster. And if we insert every edge, we insert an edge to every non-edge here, and we get a clique of size 6. But this structure will be obviously be solved by our reduction rule, because we do brute force on every connected component of size 6. The following are some examples of the possible structures to form a clique of size 5 in final cluster graph. And in the following pictures, some cases it returns no. In some cases, we will merge C1 and C2 into a clique, and maybe C3 and C4 into a clique of size 3. And in some case, it will be possible to form a clique of size 5, because we can merge C1 and C2, C3 into a clique, or we can merge C4, C2, C3 into a clique. But however, we will show, we note that in all the structures, it is also a component of size at most 6. So this will be solved by our brute force algorithm, brute force reduction rule. So the remaining case are the cliques of size 4. But this will be a bit more complicated than before. So this is a possible structure of to form a C4 in the final cluster graph. X and Y are cliques, are protocluster of size 1, and these Z1 and Z2 are protoclusters of size 2. So according to the structure we showed just now, we get reduction rule 7 to deal with the structures to form a C4. This following picture shows some examples of reduction rule 7. In the first case, our reduction rule is to delete all the edge vy and delete the edge xu. Then we insert an edge to xy. So we get a click of size 4 in the center. And in the second case, it will return no, because there is no proper edits such that the L equals 0. In the third case, we delete these two edges, that is yz1 and yz2. We delete uw, and we will insert an edge to xz1. We get a click of size 4 in the center, and we get a click of size 2 here. In the fourth case, it is symmetric to the third case. We delete the edges here, and we will insert an edge here. We get a click of size 4 in the center, get a click of size 2 here. And in the last case, we will replace the whole structure with a path. And this path consists of two packed P3s, that is VAB and PCW. Note that after applying the reduction rules 1 to 7 exhaustively, the sizes of the clicks are at most 3 in the final cluster graph after applying the solution. Then after applying the reduction rules, we show that the remaining instance of CATMP is equivalent to an instance of a variant of cluster deletion, which only allows edge deletions. So this definition is also very similar to the CATMP problem, except that we only allow edge deletions, we do not allow edge insertions. Because the structure will become very simple after the reduction rules. Then we show this instance of CDAMP, that is cluster deletion, can be reduced to an instance of 2-set, which can be solved in polynomial time. This is our lemma. We can construct an equivalent instance of 2-set if and only if phi is satisfiable. Let's introduce some how we construct this 2-set instance. And after applying the reduction rules 1 to 7 exhaustively, we get an instance of CDAMP. Then we construct an equivalent 2-set formula phi as follows. Let EC be the set of edges which are covered by some P3s of the packing H prime, and let lambda be twice the size of the packing H prime. We label the edges of the of EC by E0, E1, and E lambda minus 1 according to some arbitrary ordering. First, we initialize the 2-set formula phi as true. Then for each induced P3 in the packing H prime, if xy equals EI and yz equals EJ, then we add the two clauses xi or xj and not xi or not xj. Roughly saying, this means that for every packed P3 xyz, we delete exactly one edge, that is xy or yz, in this packed P3. And for each induced P3 UVW, such that UV and VW belong to two distinct P3s of the packing H prime, then if UV is EP and VW is EQ, we will add a clause XP or XQ. This means we have to delete at least one edge in this P3 UVW. Roughly saying, if we assign 1 to the variable xi, then this means we delete this edge of xi. So this finishes our XP polynomial time algorithm. But then let's conclude with some open problems. So the first open problem is We want to ask if there is an FPT algorithm parameterized by L for the problem CEATMP. We have shown this problem is in XP. However, it is still possible to be FPT. But we need some more structural insights into this problem. The second problem is that what is the computational complexity of other variants of cluster editing above modification-disjoint P3 packing, where every vertex is instant with at most C packed P3s. C is larger than 2, but smaller than 23. Okay, maybe some people is interested in this problem. That's all. Thank you.
All right. Thank you so much for the talk. And I guess we can take some time for questions. So are there any questions? If you have any questions, you can just unmute yourselves and ask, or if you prefer, you can type in the chat. All right, I'll just ask one. So have you also tried any other problems with this kind of a lower bound? Like other than this one, other than for cluster editing?
We saw some, for this, we studied this problem is motivated by the open problem proposed by Komshevich, and actually they had some similar result of like triangle packing, or as far as I remember, or some or some also F deletion problem.
Okay.
But their result is somehow because they show that if the lower bound is vertex disjoint P3s, then this problem is FPT.
Okay.
But we show that we give a negative answer to this question.
All right. Okay, thanks. Let's just wait a few seconds if there's any question. All right, I suppose not. All right, then let's conclude here. So thank you so much for the talk once again. It was really nice to have you.
Okay, thank you for the invitation.
Yeah, and yeah, thanks to the audience for being around. So we conclude the session for today here, and see you all next week. Thank you. Bye.
Bye.